Have you ever wondered how the universe began? It's a question that has intrigued humanity since time immemorial, a riddle wrapped in the enigma of the cosmos. The birth of the universe, its origin and its seemingly infinite nature are mysteries that have both baffled and fascinated us. One of the most widely accepted explanations for these conundrums is the Big Bang Theory. The Big Bang Theory proposes that the universe we know and marvel at today started as a singular point, an incredibly hot and dense singularity, around 13.8 billion years ago. From this singularity, the universe expanded, giving rise to the cosmos we now explore with our telescopes and satellites. But the Big Bang Theory wasn't born fully formed. Like the universe itself, this theory has evolved over the years. Initially, it was met with skepticism, even outright rejection. Yet, as more evidence came to light, the scientific community began to see the Big Bang Theory as a compelling explanation for the creation of the universe. The discovery of cosmic microwave background radiation, the redshift of distant galaxies, and the abundance of light elements like hydrogen and helium all pointed towards a singular explosive event that marked the birth of the universe. Each piece of evidence added another stitch to the tapestry of the Big Bang Theory, turning it from a controversial idea into a cornerstone of modern cosmology. The Big Bang Theory is not a mere hypothesis, a wild guess thrown into the cosmic wind. It's a theory in the scientific sense of the word, a well-substantiated explanation of some aspect of the natural world that is acquired through the scientific method and repeatedly tested and confirmed through observation and experimentation. And so, as we delve deeper into the mysteries of the universe, we're not just investigating physical phenomena, we're unraveling the story of creation itself, a story that science has stitched together through the Big Bang Theory. The Big Bang Theory is not just a theory, but a story of creation that science has stitched together. Picture this, an incredibly dense hot point smaller than an atom. This, my friends, is the singularity. The singularity, a concept that might sound alien to many, is in fact a cornerstone of our understanding of the universe. It's a point of infinite density and immense heat, a point so small that it defies our understanding of size. It's a place where our conventional laws of physics cease to apply, and where time and space as we understand them simply do not exist. This is the starting point of the Big Bang Theory, but what does that mean? Well, it means that at some point around 13.8 billion years ago, all matter, all energy, everything that makes up our universe was concentrated in this minute point, this singularity. It's hard to fathom, isn't it? A point so small yet containing so much. And it was hot, extremely hot. We're talking temperatures in the billions of degrees. So hot, in fact, that matter as we know it, atoms, molecules, the stuff that makes up you and me and everything around us, couldn't exist. Instead, the singularity was filled with a dense, hot soup of subatomic particles. But why does the singularity matter? Well, it's because the singularity is where our universe began. It's the starting line of the cosmic marathon that is the history of everything. According to the Big Bang Theory, time and space as we understand them started at this point. Imagine the singularity as the seed from which the tree of the universe grew. From this incredibly small, incredibly dense point, an explosion of unimaginable scale occurred. This explosion, the Big Bang, was the birth of our universe. From this singular point, an explosion of unimaginable scale occurred, creating what we now know as the universe. In a split second, the universe expanded faster than the speed of light. Let's just pause for a moment to appreciate the sheer magnitude of that statement. This mind-bogglingly rapid expansion of the universe from the singularity is known as inflation. Now you might be wondering, how can anything move faster than light? That's supposed to be the ultimate speed limit, right? Well, the key here is that it wasn't matter moving through space, but space itself that was expanding. This allowed the universe to get around the speed of light limitation. This period of inflation was incredibly brief, but it had profound effects on the universe. The inflationary period allowed the universe to smooth out any irregularities, leading to the remarkably uniform universe we see today. But it didn't just make the universe bigger and smoother. As the universe expanded, it also cooled down. This cooling was critical for the next step in the evolution of the universe, the formation of matter. Prior to inflation, the universe was so hot and dense that particles couldn't stick together to form anything substantial. But as the universe expanded and cooled, conditions became just right for the formation of protons and neutrons, the building blocks of atoms. But of course, protons and neutrons aren't much use on their own. They needed to come together to form atoms, the building blocks of everything we see around us today. And this is where another fundamental force of nature comes into play, the strong nuclear force. This is the force that holds the protons and neutrons together in the nucleus of an atom. So in this incredibly brief moment of time, the universe underwent a dramatic transformation. It went from a hot, dense point of singularity to an expansive, cooling universe. It set the stage for the creation of atoms, the building blocks of matter, and ultimately, the formation of stars, galaxies, and everything we see around us today. As the universe cooled, it gave birth to the fundamental particles and forces that govern our world today. And that's the story of the expansion of the universe. Post-expansion, the universe turned into a cosmic soup, a hot, dense sea of particles. In this primordial stew, particles of light, known as photons, were trapped, incessantly colliding with free-floating protons, neutrons, and electrons. As the universe expanded further, it cooled. And after about 380,000 years, it had cooled enough to allow these photons to escape. This period, known as the Era of Recombination, marked the birth of atoms, specifically hydrogen and helium. These atoms, light as they were, began to clump together under the influence of gravity, forming clouds of gas. Over the course of hundreds of millions of years, these gas clouds grew denser and hotter, until at their very heart, nuclear fusion ignited. This was the birth of the first stars, brilliant and short-lived. The death of these early stars was as significant as their creation. In their final throes, they spewed out heavier elements like carbon, nitrogen, and oxygen. These elements, essential for life as we know it, were scattered across the cosmos, ready to be incorporated into new stars and planets. Meanwhile, the universe continued its relentless expansion. Over billions of years, gravity choreographed the dance of matter across the vast cosmic stage, pulling gas and dust into swirling galaxies. These galaxies, each a glittering metropolis of stars, planets, and other celestial bodies, are the building blocks of the universe's large-scale structure. As we look out into the universe today, we see a cosmic landscape sculpted by these processes. From the smallest atoms to the largest galaxies, everything we see is a product of that initial expansion and the subsequent cooling and coalescing of matter. The universe, once a dense singularity, had become a cosmic soup. It then transformed into a sea of atoms, then stars and galaxies. It's an evolutionary process of astronomical proportions, a testament to the power of time and the laws of physics. From a singularity to a cosmic soup, the universe was beginning to take shape. The Big Bang theory has stood the test of time, yet it continues to evolve. This remarkable theory, first proposed in the early 20th century, has been supported and strengthened by various pieces of evidence. One such piece of evidence is the cosmic microwave background, or CMB. This is a faint glow of radiation that permeates the universe, an echo of the heat from the Big Bang itself. The CMB is incredibly uniform, suggesting that the early universe was too, which aligns perfectly with the Big Bang theory. Another compelling piece of evidence supporting the Big Bang theory is the redshift of distant galaxies. When we observe galaxies far away, we notice that the light they emit is shifted towards the red end of the spectrum. This redshift indicates that these galaxies are moving away from us, and the further they are, the faster they're moving. This observation suggests that the universe is not static but expanding, a key tenet of the Big Bang theory. Despite the robust evidence supporting the Big Bang theory, there remain unanswered questions. For instance, what caused the initial singularity to explode? What happened before the Big Bang? These are questions that modern research is trying to answer. Scientists are using cutting-edge technology and innovative approaches to delve deeper into the mysteries of the universe's inception. One such area of research involves gravitational waves, ripples in the fabric of space-time caused by violent cosmic events. Detecting these waves from the early universe could provide valuable insights into the Big Bang and the moments immediately following it. Another exciting area of research is the study of dark matter and dark energy, mysterious entities that make up a significant portion of our universe but remain largely unknown. The Big Bang theory is our best explanation of the universe's origin, yet it's a story still being written as we continue to explore the cosmos.